Right. So, good morning, good afternoon, and good evening. Um, I'm Jun'ya Kume, a postdoc at the University of Padova, working on the gravitational wave physics and cosmology. So, first of all, let me thank to the organizers for providing this opportunity to give this talk. And the title is Gravitational Waves and Black Holes from Catalyzed versus the Phase Transition. And this talk is based on this paper in cooperation with Ryusuke Jinno and Masaki Yamada. Okay, so let me start from an introductory part on cosmological first order phase transition and its gravitational waves. Then I'm going to explain our scenario and its observable signatures. Okay, so let's start. And in modern particle cosmology, it is widely accepted that our universe undergoes phase transition in its thermal history. And depending on the model of particle physics, such transition might be a first order. And what's special for first order phase transition? Microscopically, it is described by the quantum tunneling of some scalar field trapped at this false vacuum. And this quantum tunneling predicts the nucleation of bubbles inside of which scalar settles down at this true vacuum. And once nucleate, this bubble expands and enter into the macroscopic regime. And in this regime, we can simply regard the bubbles as expanding boundary, having and releasing energy. So they are steering plasma, and we can expect gravitational waves from this violent phenomenon. And actually, production of gravitational waves from first order phase transition has been widely investigated. And to characterize this macroscopic dynamics, we typically introduce these four parameters, which is ultimately determined by underlying theory, but at the same time, which determines the power and spectrum of the gravitational wave signals. And there are three expected contributions to the gravitational wave background, and two of them, which are believed to be dominant in most cases, are analytically and numerically well understood. But in fact, it's not that easy to have an observable gravitational wave background from first order phase transition. And here we propose a new and a bit non-standard scenario, which naturally predicts larger bubble sourcing larger gravitational wave signal. And this can be proved by future gravitational wave observations. So we are quite happy to give an interesting prediction. Okay, so now let me explain how to realize collisions of large bubbles. And our key ingredient is compact objects in the early universe. Okay, so I'm not going into the detail, but the nucleation rate of bubble can be calculated from the effective potential of scalar field, which is called as bounce action. And the point is that compact objects having strong gravitational effect can be impurities to this phase transition. which significantly enhances the tunneling rate or the bubble nucleation rate. And in this work, we assume black holes as such impurities. And for black holes, we can naively expect that the gravitational enhancement of this nucleation rate becomes efficient when this relation holds. I mean, the correspondence between the radius of black holes, so the radius of black holes and the radius of the bubble, which is determined by the particle physics scale. So we need, in this case, we need a really tiny black holes, which may be formed in the early universe. Okay, and here's an assumption we made for our scenario. And first is on particle sector or the nucleation rate. In short, we assume that bubble nucleates only around primordial black holes like this. And this is because of the gravitational enhancement. So we can say that in our scenario, primordial black holes are the nucleation site. And the second assumption is on the distribution on the primordial black holes. And for this one is just for simplicity. And we take a monochromatic mass of the primordial black holes, which are formed at some initial time, Ti. And here's the important assumption. And here we introduce an epsilon parameter, which is the averaged number of primordial black holes per horizon volume. And we require this to be much smaller than unity at nucleation. And with this sparse distribution of nucleation site, bubble can expand up to the horizon scale until they collide much later time. So in this way, we can naturally, under these assumptions, we can naturally expect the collision of large bubbles, which sources stronger gravitational wave backgrounds. But this is just an idea. So in our paper, we examine the such the phase transition can consistently take place. And the most important check is whether or not transition completes. Otherwise, the universe starts to inflate and becomes inconsistent to what is observed. And here, two macroscopic parameters involved. And the first one is beta, depends on this number density of primordial black holes and volume swept by bubbles. And this roughly gives the inverse duration of f of pt, first order phase transition. And we assume another parameter alpha to be small enough. In fact, this is related to the latent heat of the phase transition. And this is to avoid a forced vacuum domination. And then we find that phase transition successfully completes. And at the same time, we give a universal prediction on this value of beta to be 3 at the time of bubble collision. But in fact, this small alpha is important for another way, because this is not the end of the story. So there is an interesting product from this scenario. So although phase transition completes, there are statistically rare patches that those do not contain bubbles or black holes. Then, some late time, vacuum energy starts to dominate there, and the patch will be causally disconnected by the accelerating expansion. And this baby universe, seen from the outside, or our universe, finally closed by an event horizon, which is a birth of a baby black holes. So this scenario predicts the production of baby black holes, and its abundance depends on this value of alpha, which is crucially related to the power of gravitational wave signal. So let's see. So let's see how large gravitational wave signal we can have for the case satisfying all the constraints. And now I'm going to explain the gravitational wave background expected from this scenario. And the point is that we can connect first order phase transition parameters to the parameters of seed primordial black holes. So here's a golden formula for gravitational wave background from a bubble collision. And as I said, beta is universally determined in our scenario, but we also need to fix this alpha and T collision, which is related to the frequency of the peak of the spectrum. And we have two parameters for primordial black holes. This is commonly used in the literature, but the latter one, beta, is nothing but epsilon in ours. Epsilon in ours, okay. So, and in fact, T can be determined from this collisional condition, but alpha needs certain consideration. And in this study, we made a rough order of magnitude estimate, making use of the relation between the particle physics scale and the black hole radius to have an enhancement of the nucleation rate. And in the end, we can express these parameters in terms of primordial black hole parameters. Then let us apply the bounds on primordial black holes to the baby black holes or to the alpha parameter. And assuming the Poisson statistics, the abundance of baby black holes expressed by alpha in this way, and also its mass is given by the masses of the seed primordial black holes. And here's the constraints on the primordial black hole abundance. And from this, we can project these constraints on the MPVH and alpha plane through this relation. And this gives the largest allowed amplitude of gravitational wave backgrounds without baby black hole overproduction. And using the relation mentioned before, we can also get the peak frequency of gravitational wave corresponding to this to each maximum alpha value. So we can compare the predicted signal to the detector sensitivity like this. And so this region is viable and probable part. And with this comparison, we can finally get a viable parameter space of PBHs for this scenario. So using this, we can get the contours of T collision and also alpha. And then we can use the golden formula to convert it in omega GW and its peak frequency. Then we can get we can get the sensitivity curve of detectors in this PBH parameter plane. And as a main finding, we identify a regime where we can get observable stochastic gravitational wave backgrounds, and at the same time, the dark matter abundance can be explained. So this will be the region where baby black holes become can be the whole dark matter, and at the same time, we can have observable gravitational wave signals. Okay. Let me summarize my talk. So the point is that compact objects can gravitationally enhance the tunneling rate. And so primordial black holes may act as a nucleation site of the first order phase transition. The smallness of, and if the small number of primordial black holes per horizon realized, we can have a situation where the horizon size bubble collides, which predicts large gravitational wave signals. And at the same time, baby black holes are produced. And we have identified the parameter regime of the seed black holes, where we can explain the dark matter abundance by produce baby black holes. And at the same time, observable gravitational wave backgrounds are produced in the scenario. Okay. And here's things to be discussed. And the first and most difficult part would be the feasibility or about the feasible particle physics model, because there is a really non-trivial assumption we made. So far we have only in mind dark sector or vacuum transition. But it would be nice if we can find another models or possible realization in the particle sector. And we can also consider other types of impurities. So compact objects should work similarly, I mean, other than black holes. But once if we consider, for example, defect network, they have some non-trivial spatial distribution. So it might be interesting to think whether we can get some differentiable signature from this spatial distribution. Okay, so that's all from my talk, and thanks for your attention.